Hello friends, let's discuss about the final design that we discussed in the previous video about our matching engine. So as we discussed in the previous video that we will be maintaining priority queues just for the price levels. What I mean is that for this price level, right, we have got a price level of 20.3, 20.25 for sell, and similarly for bid or buy, we have got these two price levels. So we will maintain two priority queues, each for sell orders, for asks, and another for the buy and the bids. So two priority queues, which will be just maintaining the price levels. And for each price level, we'll create a map, which would be a doubly linked list. Doubly linked means that for each node, there would be a previous and the next link. And in this doubly linked list, for each price level, that would be maintained in a map. And in that map, the key would be this price, and which is a double, and the value would be the actually linked list, the doubly linked list, containing the best time priority at this price. Because as we know that for our matching engine, the logic is always based on price and time priority. If the price is same for two orders, the order which has come first, it has got a better time priority. So this order would be matched first before the order 2, because this order arrived at say 905 and this order 1 arrived at 901. That's why it has got higher time priority. Please note that the price is same for both orders. It's only based on the time now, and that's why we are maintaining this doubly linked list for at the same price level. So as mentioned, we will maintain the price priority key for the price levels, for maintaining price priority. And whenever a price is found, best price is found, we can use a hash map with key as price level and value as linked list, doubly linked list of orders at that price level. And the head of the linked list, right, this would be containing the best time priority orders, and that's why this will be executed first. So in my GitHub link, you can see that I have got this Q11 matching engine, which is for the this 11 problem. And there is a folder subdirectory called as final solution, in which we have got order book and order list. So let me go through the data structure that we are using in our final implementation. So let's go to the order book, which is implementing an interface. In this interface, we have got add order, print level 1, print order book, cancel order, amend orders. We have got 3 versions for it. Based on the order ID, you can change the quantity or the price or both of it. And then we are also maintaining an order cache, in which we are maintaining key as order ID and the value as the actual order. So let's go back again here. So as we discussed, right, that for each price level, we will maintaining priority queues each for buy and sell. So this is what we are doing here. So we are having 2 priority queues for buy price levels and sell price levels. And as we know that for the buy order, for the buy side, the order having the highest price is having the highest priority. And similarly for the sell price levels, the order with the lowest sell price is having the highest priority. So that's why for buy price levels, you can see that I have used a comparator.reverse order, because by default the priority queue is always in an ascending order. For maintaining the for the buy price levels, we need a descending level, because at the head we want that it should be having the highest priority for the bid. That's why we are reversing it, so that it's always in the descending order. For sell price levels, we will take the default, which is ascending, which means that the head of the sell price level would be always the lowest sell price, and having the highest priority. Now here goes our main implementation logic, which was different than the previous implementation that we have done. Here we are maintaining this map of each price level. For example, we discussed that for each price level, we will be maintaining a doubly linked list, which I have implemented as an order list here. I'll go through it again. And it will be containing, the head would be containing the best time priority order in that. So let's go to the order list. And order cache we already discussed that we'll be using for amendments and cancels. So let's go to the order list here, which is here in my second class. So as I mentioned that this is a doubly linked list, in which we can see that each of the node, I'm creating a private static class here just for the ease of it. It would be having the order, the actual data is the order itself, and we will having a previous and the next link, which is a property of a doubly linked list. And then we actually create this by using this constructor. Okay, so If I don't provide anything here, it means that the previous and next would be null. So if we have implemented any like linked list using data structure using Java, it's very similar to that. What I have done is that I'm maintaining extra size and total volume. What I want is that for each price level, what is the total size of orders? There can be multiple orders, right, in the same W linked list at the same price level. For example, in this diagram, right? So, for example, at 20.3 price level, I can see there are two orders. One is of quantity 100, and another is quantity 200. What I want is that at this price level, what is the total volume available? So it would be 100 plus 200, which is 300. So this is what I'm maintaining here. And so this was total volume, sorry. And the size is actually that how many number of orders are there. So size would be, in this scenario, would be 2. For 20.3, it would be this 1 and 2 orders. And the total volume would be 100 plus 200, that is 300. Similarly, at 20.25, it would be 100 only. And the size would be 1. Similarly, we can do it for the same bid. Now I've created this extra add head method that when we want to add an order at the head of our linked list, which means that we want to add just immediately at this point here. So it would be add head. Similarly, add tail would be done at the end, at a tail of the linked list. Ideally, I mean, this diagram should be showing having a double links, one to the previous and one to the next. So just for the sake of brevity, just take it as it is. So add head, add tail. I mean, you can go through the implementation details. I will not go through it because it's just a simple doubly linked list implementation in Java. And in each of these cases, as I mentioned, that whenever I'm adding any order to our doubly linked list, I will be increasing the total volume, which is the order quantity, and the size. This we want because many times in interview questions, we have to implement a design that we want to know that at a certain price level, what is the total volume available there of open orders and how many number of orders are available. So this would be helpful if you maintain these two total volume and size properties. Similarly, this is a very important method for get head because whenever we are matching, whenever we found the best price, we will always take the head because that would be the best price time priority for that particular order to match at that price level. That's why this get head method is very important for matching of the orders. And here its implementation is quite simple. So once we are getting the head, because we are returning the order out of it, we are going to remove it. So while removing, I will decrease the total volume and the size. Similarly, we need a remove order. This would be needed for cancellations or amends. And remove node is very much similar to remove order, but only thing is that I have made it like remove order is like I made it public. Implicitly, it will call remove node because that order is represented as a node inside my doubly linked list. So only when you want to like cancel any order or remove any order, we are just exposing this method to the client, which marked as public. Inside it will be calling remove node here. Okay, so remove node is, we are, in this cases, just remember that we are already taking all the edge cases that if it's the head or it's a tail, then how the new head would be created, or if it's a tail order, there would be no next link. So how it will be updating the head and tail pointers. So this is all implemented here, taking all these edge cases. Similarly, peak head will not remove anything. It will just check at the top of the what is the best price time priority available at that price level. And get orders will say is simply that if you want to like display the level 1 or level 2 or that all the orders at that level, it will iterate through the list and then display it. It will just not display it, but just give us the list, simple list, array list. And then we have got getters and set and this is the print list, which I just mentioned that it will go through it and then it will print all the orders. This will be required when we are trying to display the level 1 or level 3 that we have discussed in our previous implementations. So guys, this was the discussion about our basic data structure design, that how we are going to implement our final implementation. In the next video, we'll go through addition of order, that how when we add any unfilled order, whenever we receive an order, what are the conditions that we are matching it, and if there's any unmatched quantity, how we are adding it back to the order book. So let's discuss all this in the next video.